Well, hello again. This is Eric Spiller, and this is going to be a lecture on classification. It's lecture 5-2 in the plan for this class. So let me share my screen. And here it is. And we'll get started. Uh, Classification. You've heard the term. We talked about classification in the lectures on crushing and grinding and liberation. Well, classification is separating particles based on their size, and it's usually done to provide unit processes that come along following the classification material that is prepared for those unit operations. So the big umbrella word is classification, and then there's a number of ways to do the classification where it needs to be used. And of course, you can see on this slide the scalping. We're trying to get rid of coarse material so that it prepares the feed for presentation to some sort of separation. We term the word scalping to get tramp oversize out. We grade the material if you have to have particles of certain size and shape for perhaps making glass sand or for road aggregate, that sort of thing. We use classification for the washing and sizing in a heavy media preparation plant, and we dewater and deslime using classification. So we're going to go through these slides fast, and we might skip a few of them because we don't really have time. I want you just to get the general idea of what sort of things we're talking about. So we can screen, put material through a sieve opening. We can use hydraulic systems where we have upflowing water currents, and the upflowing water carries the fine material up, and the coarser material goes to the bottom, and we extract it somehow. And then we can use hydrocyclones, which we have talked about before, but hydrocyclones are really, really big for making density separations. So let me just review what a hydrocyclone is. We have a unit that is a barrel usually with a cone at the bottom, and we have a pipe that sits down the center. That pipe is called a vortex finder. And I just want you to know what these are because you'll see them in a plant. The underflow down here is the apex or the spigot. Feed is introduced up here under pressure. We'll call that the way it's designed. And then out the top here, this is where the out that's picked up on the vortex finder, this is the overflow. And what comes down here is the underflow. Comes out through the spigot. So if we think about this, there's many of these used. So the feed comes in, the slurry, and it's a mixture of, in the case of a classifier, we assume that it all has the same specific gravity. We know it doesn't, but the material comes in and it creates a cyclonic effect like this coming down through, and the coarse material, due to the cyclonic activity, the coarse material goes out the side, comes down here and comes out, so we have coarse coming here. The fine material doesn't get thrown out quite so much, and it escapes through the low pressure up here and the overflow, and it's the fine. Now, if there is some heavy minerals in there, along with, say, quartz, This also becomes a bit of a concentrator. So we have the fine lights up here, and we have the coarse heavies as in specific gravity, and lights as in specific gravity. So if we are using a cyclone to make a gravity separation, we have to have all the same particle sizes. And if we're using a cyclone to make a size separation, then we should have, everything should have the same specific gravity, all the particles. You never have that in the real world, but anyway, that is the hydrocyclone, and I just wanted to make sure that we had talked about that. We use it in liquid solid separation. That's a type of classification. We have to use it for controlling density and flow sheets, and it's obviously a part of tailings management. So screening, that's the big one. There is, we use screens in a lot of places. We have coarse screens and fine screens, and the definition of those are you know, they overlap. We have steel screens, we have woven cloth, we have perforated plates, we have polyurethane, we have a lot of different types of screens. We can do it wet or dry. We have methods for sizing screens. You know, how big a screen, how many feet wide, how many feet long, how many meters, what is the capacity, what is the feed pulp density that we put onto screens. That's all engineering stuff. We have screens that that make a separation. They don't move. They make a separation just by particle passage through the hole. And we have screens that are probability. What is the probability of a particle of some size going through the hole? We have screen decks that move and vibrate. We have conventional ones there again, and we have probability ones there again. Vibrating screens are by far the largest group. Making fine separations have a higher frequency of vibration than making coarser separations. So grizzlies, we've talked about grizzlies in the context of jaw crushers earlier in the modules, and this is what you've seen this picture too. There's a grizzly screen protecting a jaw crusher. That's a type of classification, relatively coarse separation. We have sieve bends. This is a probability machine that's based on a curve. We won't get into much about that, but this is what it looks like. You can change the angle on them. You get different pulp densities coming down. They vibrate. They don't vibrate, but this is a sieve bend design screen. This is your typical coarse screen used with the feed coming in. Obviously here, you scalp off the coarse material. You have an intermediate material. You have a bit smaller material, and then you have coming out underneath. I don't know how to draw this, but anyway, coming out underneath, you have the fine. So this top one is primarily a protection for this one. This is a working screen, and this is a working screen, and so this would be pretty much mid-size, and this would be coarse, and this would be tramp. And there's many of different parts to this sort of a screen. Fine screening, we're getting better and better at fine screening. We have commercial screens now going as fine as 75 microns, even finer. And these screens now have months worth of time before they wear out. That used to be a big, huge problem with fine screening, but the advent of polyurethane screens and run at high frequency and low amplitude has extended the life of screens immensely, and it's made them conceivable to be used inside of grinding circuits. Still probably 80–90% of the classification in a grinding circuit utilizes hydrocyclones, but there's more and more instances of it using screens. As I said, the most screening in the fine sizes is done wet, although there is dry screening done. And you know, we need dry screens. We don't want a wet material if we don't have to wet it, and especially if we have unit operations downstream from the screens that's a dry. So we don't want to dry it because it's expensive to re-dry. There's ways to, you know, what is the feed rate? How, you know, how does it affect how, if you know, it affects the efficiency of the screen, the capacity of the screens. You have to buy more screens, that's more dollars. So best, well, it's just simple. Capacity is best determined by screen testing by the manufacturers. Feed density, it's kind of interesting that if you have a screen and you're feeding it, and the material that comes off at the top here, it can or cannot be divided like this, but it's really the material that follows the water through. So the water goes through the screen, it takes the fines through, and then you almost have to add more water down here, sprays, to get more material to come through, and then of course the coarse and the fines come out of this. This is the coarse and this is the fine down here. Water is important on a screen, and it changes the operation quite a bit. Obviously, how much near size material you have, that's material that's close to the same size as the aperture. The more of that you have, the more chance you have for blinding, and for lower capacity. All of that is, you know, is important in the design. The amount of open area, you know, if you have a screen and you make it out of wire, compared to having the same size of openings made out of, you can see here, you know, made out of, instead of wire, I think railroad rails or something. But you can see the amount of space that's taken up here if you have wider. So the amount of opening, the amount of opened area for the same size, these are all the same size, but here you have, you got 2 openings, and here pretty much in the same area, you've got 6 openings. That's obviously going to have higher capacity. It's also a lot more fragile than this. This is robust, and this is fragile. Just the way design works. These are wet pulpers, you know, with the sprays on them. These are fine screens, high capacity. These urethane panels and vibrating motors. That's all part of patent protected technologies that the screen manufacturers have. Urethane screens, these are, like I said, they're becoming very important and being used a lot more. So in grinding circuits, if you have a hydrocyclone, you'll end up with misplaced material. Remember I said there was the gravity issues. So you'll get coarse material, you'll get fine heavies coming to the cyclone underflow because it's a heavy specific gravity. You don't necessarily get a particle size cut. And so this is a stack sizer. It's one of Derek's machines, and they're yeah, I can't remember that's spelled right. Anyway, the Derek screens. This is there's five. Well, there's five. 1, 2, 3, 4, and 5 down here. I think maybe it's 4. Anyway, there's a number of screens in this one unit, and you can get enough capacity in this and newer models of this to go into a grinding circuit. And this is a grinding circuit where they took a cyclone out and put in a screen and then looked at the performance on this. And when they did that, they were able to increase the capacity. You can see that went up. You can see the power draw went down. You can see the circulating load. Remember, we talked about circulating load in grinding circuits. That came way down. The circulating load on the minus 71 microns came down low. The percent grade, the circulating load, how much iron was in the circulating load, which you don't want, that went down. The concentrate grade remained the same, you see, and the iron recovery went up slightly. But the big thing here is much better performance as far as power draw and capacity. There you go, more tons, 145 tons per hour, and you still had the same grade and the same, essentially same or better recovery of iron. There's other examples you can look up. Hydraulic classification is the upflowing water, and it's not perfect, but certainly is being used a lot around the mineral processing industry. And it's basically smaller particles fall more slowly in fluids than do larger particles if they've got the same specific gravity. And so there's a number of different kinds of units. In the olden days, we had rakes and spirals that were used for hydraulic classification. They can be used mostly with water, although there is some classifiers that are dry that use this flowing motion and the settling motion of the smaller particles. And so I'm not going to get into this, but I do want to talk about these fluidized bed hydraulic classifiers, because that's something that's relatively new. We'll just skip the hindered settlers. And this is the unit here. And basically, I'm going to show you what's inside, but you can use it to actually concentrate. So you can get contaminants such as coal and lignite and peat. You can have it. That's a light specific gravity. So if you have upflow, you've the bottom of a column, the material going over the top is going to be fine, and the material coming out the bottom is going to be coarse. It can be used in getting rid of silts, but it also can be used to prepare feed for a spiral concentration circuit. It's pretty simple the way it works. There's other machines. I put this in here. There's the Linatex machine, there's CrossFlow machine, and this is a Flotex. They all are teeter bed machines. You have feed coming in here, you have these pipes sitting about here, and you inject water through these pipes, and the water is rising up because you have this overflow here. And the overflow is the fines or low specific gravity material that comes out over the top, and the coarse material comes out the bottom. And what you have is this material comes in and goes and starts settling. It encounters this water that's going in this direction, and there's a teeter bed that sits here with size material that just kind of doesn't know where to go, and it sits there, and it's almost like a filter in the way that it works. So it teeters, called a teeter bed, then, and it's pretty well controlled because you have a pressure sensor here, and then that pressure sensor works a valve down here that that changes, that opens and closes the bottom as you have a constant feed of water coming in, which causes this upflow action. Anyway, there's many new designs of these type density classifiers, and they're very, very accurate, and they make a very, very good separation based on size with a little density flowing in. This is an overflow on a Flotex unit operating in Norway on a titanium plant. And that's the end of the lecture. So classification, we do it with screens, we do it hydraulically, we do it in hydrocyclones. Classification is the umbrella term for separating coarse particles from fine particles. And thank you. I'm going to stop the share and stop the recording.